This is the fourth video on section 7.7, triple integrals. And so here in example 238, we're asked to use a triple integral to calculate a volume. Now remember, when we were looking at double integrals, we used a double integral to calculate an area. And to do that, we use the fact that integrating over a region under a function gives us a volume. And so what we did is we integrated the constant function 1 over our region in R2, and that gave us area. So we're going to do a similar thing here. We're going to integrate the function 1 over our region in R3, and that's going to give us a volume. And so we're going to set this up as a type 1 region in R3. And so we're told that T is the tetrahedron bounded by the coordinate planes, x equals 0, y equals 0, and z equals 0, and this plane, x plus y plus z is equal to 2. And so the plane z equals 0 is simply the xy plane. And the plane x equals 0 is simply the yz plane, and then the plane y equals 0 is simply the xz plane. And so we're looking at the three coordinate planes and this plane here. And so this tetrahedron, I've drawn it right here. We have the point 2, 0, 0, 0, 2, 0, and 0, 0, 2 on this tetrahedron. And we're going to integrate over that. And so what we have is we have z goes from the xy plane up to this tetrahedron. And so z goes from 0, well, to this function. Z here is a function. And so if we think back to how we define this as a type 1 region, this function here, this is our g2. This is our upper function of x and y. And the g1 is 0. So we're going to integrate from 0 up to this function right here. I'll jump ahead a little bit. So z goes from 0 up to that function. Now, the reason it's important to draw this and know what this looks like is now we also, in the end, have to integrate over our projection of this tetrahedron onto the xy plane. And so when we do that, we're going to set that region up as a type 1 region in R2. So we have the line segment, so the boundary right here is this line segment. So we have this triangle right here. But this line segment is one of the boundaries. That is a line segment that goes from the point 2, 0 to 0, 2. So we find the equation of the line that passes through these 2 points. It has slope -1, and it has y-intercept 0, 2. And so we have the line y equals -x plus 2. X ranges from 0 to 2. So, first of all, we set this up as a type 1 region in R3. Integrate from this constant function of x and y up to this function of x and y, dz. After we do that, now remember for that theorem, we integrated over p. That was the projection dA. Well, to do that, we're looking at that projection as a type 1 region in R2. So y goes from 0 to -x plus 2. X goes from 0 to 2. We integrate from the inside out, so we have dy dx. So now we have a triple integral. The only thing that's different from this example as our previous example is our upper limits of integration aren't constants like they were in the previous example. But given that we know how to integrate type 1 and type 2 regions in R2, this should not be too big of a stretch to figure out how to do this in R3. So here we're integrating 1 with respect to z. Find an antiderivative, we just have z. Plug in the z limits of integration. Luckily one of them is 0. So we plug in our z limits of integration, subtract. Now we have a double integral of x and y dy dx. So now this is something we already know how to do. We already know how to integrate over a type 1 region in R2. So now we find an antiderivative with respect to y. So we have 2y minus xy minus 1/2 y squared. Substitute -x plus 2 in for y. Substitute 0 in for y. Subtract. I didn't go work through the algebra here, but when you do that, it simplifies to this polynomial. Integral from 0 to 2 of this polynomial dx. This is now just a Calc 1 problem. So we find an antiderivative of this function. substitute 0, substitute 2, well, substitute 2, then substitute 0, and subtract. And so we have 4/3 as our volume.